In this portal frame we've got a lateral load being applied, and there absolutely will be sway. In another video we made an approximation to what we thought the results would be, and at the end of this video we'll go back and reflect upon the quality of that approximation. But right now let's talk about how you in detail will apply the moment distribution method to this kind of system that has sway in it. Now this next page is going to have a lot of stuff on it, so I want to reveal it to you slowly because it can become pretty overwhelming right off the bat. So what we're going to do with the moment distribution method is similarly to how we dealt with sway in the slope deflection method, and that is we have to be a little bit creative in how we do things. And what's going to happen is that big picture is that we're going to make an assumption about the amount of sway. We can either assume something about the delta, the displacement that happens, and then from that take some chord rotation values, calculate a fixed end moment that goes along with that, and then process things. Or I prefer that I just go ahead and I assume some level of fixed end moment that's convenient. That's usually 1, 10, or 100. I prefer 100. Whatever the units I'm in this case, kip feet. I let that sway happen. I recognize that both of the columns will sway by the identical amount, so their fixed end moments at the top are also going to be the same, and they would also be the same down here at the base as well, right? And then eventually what's going to happen is we'll go through, do the moment distribution with that presumed amount of fixed end moments, and figure out through the equilibrium of the whole system at the end what the lateral load was that was needed to be able to push it over, and we'll call that, say, R prime. That will not in general equal the actual value of the lateral load that we have. So what we do there is to then take our results that we get from our presumed value of R prime and then just rescale them down to our actual value of the lateral load. Right, that's the sort of the big picture of how it all works. Right, so let's take a look at some of the setup and the details, and I'm covering things up so again you don't you can kind of get focused on just the basic pieces that are here first. Just like in the gravity load case, we've got the same things with the geometry of the structure. Nothing has changed there. 600 and 600 for the columns, 14 and 14 feet for their height of the columns. I over L in units of inches to the fourth over feet would be what you see here at 42 and change. Then the beam BC has 800 for the second moment of area, 24 foot long, and its I over L is 33.33. So overall it is more flexible than the columns are. Right? Sum up at the joints what those I over L's are just at the joint alone, those things that are connected, and then that forms a basis for our distribution factor, member over the sum at the joint, likewise for the other one, and same number in this case. And then I'm just reporting what the fixed end moments are that go along with those values. Right now you look at all this stuff that is already laid out for you, and this can get overwhelming real fast. So again, let me sort of cover up some of the basic things we've got here and step things forward sort of one at a time. We've got our fixed end moments that show up on the top of the column. Right? Remember here, and take a look above, it's only the columns that have been deformed. The beam has been displaced but not deformed, so there's no fixed end moments that go along with that particular beam. Right? So we got the 100 and 100, and if you take a look, I don't want to take off the sheet of paper, but you'll see down at the bottom, oh heck, we'll do it. We'll go for it. And we've got 100 and the 100 down here, positive, down at the bottom where the column is at, base of the column. We're never going to release these down here, so that'll make things a little bit easier, of course. Right? So let's go and take a look at what the sequence of all these numbers are, sort of after the fact. Right? You always look to see if there's what has the fewest things done and what looks like a 2-to-1 ratio. And that's where you got the 4375 and 2188 are in that 2-to-1 ratio. And that tells me that I released joint B first and not C, because there's very little else happening over here at B. We've got 100 positive that becomes an unbalanced moment that has to be restored with internally a negative 100 in the combination of the two members that frame in. And according to the relative stiffness or the distribution factors here, then 56% comes over to the top of the column and 43 and change goes to the end of the beam. That negative 43.75 gets carried over to the far end because that far end is locked down, and you end up with that minus 21.88. Put the horizontal line, we've equilibrated B. Now focus your attention on joint C. You might say, hey, you're supposed to carry over something also from the column. We'll handle that here in just a little bit. Alright, so now the net sum of the unbalance at C is 100 minus the 21.88, and so that'll be a positive number. We've got to restore it with a negative, and so there we're going to distribute these back, and so that's why we have those numbers, and so that 34.18 is going to then cross back over to the far side to be the negative 17.09. Right? Again, the column will have a carryover effect to its bottom that we'll handle in a second. There's a shorthand on the page that has been done here. All right, 1709 then gets distributed by 9.61 and 7.48, top of the column and then top and to the beam. So then that will come over, and likewise, right? Equilibrate, put the line, and do that. And then we take the 374 that carried over, and we can start to set up this process of balancing things around. Now what you're seeing here, the results are all been done in spreadsheet. That's why they look so nice and pretty. But let's see what's going on and handle and deal with what's going on in the column. All right, let's take the left-hand column first. That we have 100 as a fixed end moment down at the base of the column, and you see this negative 23.08. Now if you actually looked at my spreadsheet, you'd see I would have actually carried over every one of these effects, but I didn't have enough space on the page to print that, so those have been hidden in this particular version. But another way you could have done it is note every one of these little pieces here that you see that I just put a dot onto are all from the distribution of what happens when I released the member in, well, released the joint B. And so let's see what happens if I add up all those. Starting off with 56.25 negative, plus the 9.61, plus the 0.46. Notice how fast this all went down. Plus the 0.02. That's negative 46.16. And divide that by 2, and I get a carryover that comes right over to here. Note, if I make a mistake and forget to do carryovers during the process, there's ways to recover that. So long as you haven't made a numerical mistake, you just have forgotten to do something, you can recover that. And in a sense, that's what you could say has happened here as well, that we took that net of minus 46.16 and did the carryover at the very end to get down to here. And of course the net sum is for that column, 100 minus 23.08 gives us, to the rounding at a level, 76.9 at the base. We've done the same thing over here on this other column as well, and we end up with the same kind of effect. So note here, you got to be a little careful in your thinking. The 53.8 is not supposed to be exactly double what the net in the column is, and that's because we've got a fixed end moment at the far end of the column. And another example where we were playing around with this idea of how we could do the carryover sort of at the end, we didn't have that fixed end moment down there, and so that ratio from here to here really was just 2 to 1. But that was just a carryover effect, and we've got this other piece that then modifies that a little bit. Okay, so same thing here at the top of the beam. We sum all those things up, we get the negative 53.8. Yes, that needs to be equal opposite to what we have in the column. Same thing happens over here for the beam in the column. Right, now that just gets us the end moments. From that, then we have to go look at the free body diagram of the individual member, because again, eventually what we have to figure out is what was this lateral load that we imposed to be able to get to what was that lateral load that was imposed to get to these fixed end moments of 100. Right? How does this all kind of work? So note here what I've got is this member that this stick represents, in essence, a free body diagram. That we've got 76.9 down at the bottom for a moment, 53.8, both positive, so clockwise, up at the top. And if you then take those two, 76.9 plus then the 53.8, and the column is 14 feet high, so that's 130.7 divided by 14, we should get 9.34, and that's what we come darn close to and change. About 9.34, those are the shears that go along with this, right? So if you were to go and look at then our free body diagram of our system, we get 9.34 on each of those shears, which is alone enough for us to go figure out what R prime is. Of course, we have the 76.9 for the end moments, and what we haven't done at all is figure out then what the axial forces are that are in the beam. Be easy enough to do. They're going to come from the shears in the the axial forces in the column. That'll come from the shear in the beam. We've got 53.8 at both ends of those, and that's 24 feet, so those would be 4.48 up and down for those, right? Now, the thing is, those were not the actual values that we wanted. That was a lateral load of 18.7 gives us that set or pattern of moments. What we really want is then that scaled down, so just a linear proportionality of 10 divided by 18.7 to get us the actual end moments that we want to go with the 10 kip lateral load, right? And so at some level we're done with that problem. It's kind of interesting to note that we ended up with estimating before that we thought these end moments, every single one of them would be about 35 foot kip, and they have turned out to be a little bit different, that the inflection point was not quite where we thought it would be. It's actually been a little bit higher than what we thought it would be. We could go through the math there to figure out where that would be without any difficulty, right? That would be 28.8 plus the 41.2, total of 70, and wow, 35 and 35, so that's kind of an interesting thing. And we have 28.8 divided by 70, so we're that was at the top, so we're about the 0.6 mark from the bottom is where that inflection point turned out to actually be. Now, even bigger picture part of this is that if we have lateral loads and gravity loads, then how do we handle all this? And we break them apart into separate cases is what we do, right? And so we had in a previous example, that was example M8, we did the gravity analysis. Here we just did the lateral analysis, keeping track of all the signs of everything. Then we can add everything up to get to the member end moments for gravity plus lateral, and then in superposition we can then go about and get the final moment diagram that goes with all of that as our final overall results.